What's shaken? Today we're going to continue looking at functions, and specifically we're going to look at two specific types of functions that we call even and odd functions. And if a function is even or odd, then it will have some interesting symmetries in its graph. And that's why we have these names, because these have really interesting and useful symmetries, these types of functions. So let's start by looking at even functions. A function f is called even if it satisfies the equation f of the opposite of x equals f of x for every number x in its domain. So if we have a number in its domain and we look at the function evaluated at the opposite of that number, we should get the same function value when we evaluate that function. And a classic example of an even function is f of x equals x squared. Now we can see that this looks like it might be even by plugging in a few values. For example, we can look at f of 3, which is 3 squared, which is 9, and also f of negative 3, which is negative 3 squared, which is negative 3 times negative 3, which is also positive 9. Now, this doesn't prove that it's an even function. This is just showing, if we plug in a positive value and then the negative version of that same number, we end up with the same output. It's plausible that this is even. The way that we actually show algebraically that it's even is by taking the function and evaluating at negative x, or the opposite of x. So when we do that, remember, this function squares the input. So f of negative x is going to be negative x quantity squared. That's going to be negative x times negative x. And a negative times a negative is a positive, so those negatives cancel. And we get x squared, which is the same as f of x. And so in there, we've shown that when we start with f of negative x, and we do all of the calculations and evaluate everything, our result is equal to just f of x. So that is how we show that a function is even. Now, how does this evenness relate to the graph of the function? Let's look at a very quick sketch of this graph. Here we have a sketch of the graph of the classic parabola, y equals x squared. And we know that because it's even, this says that if we evaluate the function at a positive value and its opposite, we get the same function value. This means that any point over here is going to correspond to another point over there with the same y value, just opposite x values. And what that means, same thing is true for a point over here. If we've got that point and we plug in the opposite value for x, we still get the same height. This gives us some symmetry across the y-axis. Basically, if you take the half of the graph that's on the right-hand side of the y-axis and you do a mirror image of it on the left, you reflect it across the y-axis, you end up with a mirror image on the left-hand side. So this is symmetry with respect to the y-axis, which I'll write out for us here. Symmetric with respect to the y-axis. So any function that's even is going to be symmetric across the y-axis. Can you think of any other functions whose graphs are symmetric across the y-axis, meaning the left and right-hand sides are mirror images of each other? Take a moment to think. You can even pause the video if you want. Maybe come up with 3 different examples of functions that are even. All right, hopefully you have done that. I'm going to give you a few examples. F of x equals x to the fourth is also an even function. It is a shape that looks kind of like a parabola. It's not quite, but it's much steeper and then kind of shallower in the middle. But that is another example of one that is symmetric across the y-axis. We can also look at higher even powers. G of x equals x to the sixth. That's also an even function. But there's some other ones. A constant function. H of x equals 5, or h of x equals 12, or something like that. That's a horizontal line. That's also symmetric across the y-axis. Also, there's a trig function, a very basic one, that is symmetric with respect to the y-axis. Can you think about which one that is? It is cosine of x. Also, secant is an even function. There are an infinite number of even functions. I'm not going to write all of them out, but these are some examples of functions that are even, just so that we can have looked at them. Next, I want to talk about odd functions. A function f is called odd if it satisfies f of the opposite of f equals the opposite of f of x, or f of negative x equals negative f of x for every number x in its domain. I like to say the opposite of x and the opposite of f of x instead of negative x and negative f of x, because if f of x was negative, that negative out front actually takes the opposite and makes it positive. So it's a little bit more correct to say f of the opposite of x equals the opposite of f of x, but I know that sometimes it rolls off the tongue a little bit nicer to say f of negative x equals negative f of x, though that's not the most precise way to talk about that mathematically. So this is another category of functions, and I can give you an example, probably the most classic example, f of x equals x cubed. Now, we could go through and we could evaluate this at a positive number and then its opposite, the negative version, and see if they're equal to each other. But instead, I just want to go through and use this algebraic trick to show that this is odd. Basically, if we evaluate the function at the opposite of x, and we go through and do all the calculations, in the end, we should get the opposite of whatever f of x was in the end. So remember, this function cubes the input. So f of negative x is going to be negative x quantity cubed. So that's going to be negative x times negative x times negative x. You'll note that two of those negatives cancel, leaving one remaining. It's going to be negative, and then x times x times x is x cubed. And of course, that is the opposite of f of x in this case, because f of x was x cubed, and this is negative x cubed. So because when we evaluate f at negative x, we end up getting the opposite of our original function, that means that this is an odd function. And just like the other example, let's take a look at a quick sketch of what the graph looks like to see at what happens graphically when we have an odd function. Here we have a quick sketch of the graph f of x equals x cubed, or y equals x cubed. It's not perfect, of course. I'm a human being, not a robot. But you can see basically how it looks. Maybe not perfect right here, but life will go on. When we have this relationship, f of negative x equals negative f of x, this means that if there's a point on our graph that has a certain x value, if we evaluate the function for the opposite of that, negative x, the output value is going to be the opposite of the original function value. So instead of going up however many units we are, if we look at the negative version, we're going down that many units, and we're going to have a corresponding point down there. Similarly, if we have a point up here, we're going to have a corresponding point down there, because whenever we take the opposite of the x value, we also have to take the opposite of the y value. The output becomes the opposite as well. And so there is some symmetry going on here, but it's not a mere sort of asymmetry. It is a rotational symmetry, meaning that whatever part of the graph we have over here, if we rotate 180 degrees, which is a half turn around the clock, we get the same graph rotated on the other side. We actually refer to this as symmetry with respect to the origin, because for any point on the graph, if you go through the origin the same distance in the other direction, you're going to have a corresponding point over there. So we say this is symmetric with respect to the origin. And I wonder if you can think of a few example functions that are odd, functions that have this symmetry with respect to the origin, meaning that we can take the graph and rotate it 180 degrees and get the same graph that we started with. So pause the video for a moment and see if you can come up with a few common examples. And I'm going to give you some of those examples. So f of x equals x to the 5th, or g of x equals x to the 7th are odd functions. Basically, when we have an odd power of x like that, it is going to be a graph that goes up on one side and down on the other side symmetrically. And so those are all odd functions. Also, if we have a function that's just a constant times x, that is a linear function that goes through the origin, that also is going to be an odd function because it's symmetric about the origin. And then also we have our lovely basic trig function sine of x is also an odd function. It is also symmetric about the origin in the exact same way. And in fact, this is what gives us this oddness, the trigonometric identity sine of negative x equals negative sine of x. That is because this is an odd function. Similarly, if we recognize that cosine is even, that tells us that cosine of negative x equals cosine of positive x. So some of these trig identities are related to the fact that these functions are even or odd. Having an understanding of if a function is even or odd tells us a bit about its graph, which is going to be helpful as we start applying some of the ideas from calculus to different functions.